Whenever we jump up to two-dimensional, we're going to do components, and it doesn't really add much to the momentum part of it, but it does add to the mathematics at the end where we have to combine those components to get our final answer. So sort of a classic two-dimensional hit and stick situation is we're going to consider two vehicles coming together and unfortunately crashing. I'm always going to push you to draw a diagram. I think you need to have that visual as you set up your components. We'll just take it one step at a time and see if we can put it together. This one, we've got a 1,500 kilogram car. That's going to represent my car. It's 1,500 kilograms, and it's moving 12 east. We've got a 2,000 kilogram truck moving 8 south. Not the best diagram, but that'll work. They collide, they stick together, and they're going to move off sliding across the pavement together. We'll deal with the resulting velocity first, and then we'll talk about after the collision once we get through that. I'm not going to be able to draw this too well, but we end up with a chunk of car, and then squished into that, we get a chunk of truck, and they're going this way somewhere. Again, I don't know exactly where they're going, but since I had eastward momentum and southward momentum, I know that they're going to be going somewhere east and south. We're going to tackle this with components. It doesn't matter what order we tackle them in, but our wreckage has got some southward component here and some eastward component here. I'm going to call this VE prime and VS prime. Let's start with the east-west component. The starting for a hit and stick collision is we've got our individual things that come together to make one massive object going at a common speed. In this case, I'm going to use the VE. Going back to my diagram, in the initial condition, the 1,500 its 12 was pointed in east-west components. That definitely contributes. The 2,000 kilogram vehicle was moving straight south, so it doesn't contribute anything in the east-west. So we've got 1,500 times 12. That's the contribution initially, and then after the crash, the 1,500 and the 2,000 joined together to make 3,500. We can use that to solve for that second speed. Doing a little bit of math, I'll let you crunch it out, but I got, when I practiced it, 5.1. It's positive, so that means it's in the same direction as the 12, which kind of is expected. Setting up the same thing in the north-south. Conservation of momentum for a hit and stick. We've got our individual pieces initially. They combine to make a massive object going at a common second speed. In this case, in the north-south, the 1,500 didn't contribute anything, and the 2,000 kilogram object, its full 8 meters per second, was in the south, so all of its momentum is in the north-south. So I'm going to get 2,000 times, it was going 8, equals the 3,500. Oops, and I called this one VS prime. Doing the math on that, I get that the southward component is 4.6. Now we're kind of done the physics and it turns into a component question. Nicely, it's rectangular, so the math isn't going to be too bad. We know that this vehicle with the wreckage is going 5.1 to the east and 4.6 to the south. Whenever adding vectors, connect the very starting point to the very ending point. That's going to be our unknown resulting velocity, and we'll find the angle up there. The nice way with these rectangular questions is we can use Pythagorean theorem. So our v prime squared is 5.1 squared plus 4.6 squared. Crunching up Pythagorean theorem, I got that to be 6.9. Tan function will give us the angle opposite over hypotenuse, so that's 4.6 over 5.1. Crunching that out, I got an angle of 42 degrees. Oops, this is a prime over here. Putting that all together, the velocity of the wreckage, we can write as words if we want, or if you had just written down v prime, as long as it's obvious, I would know what you're talking about. Velocity of wreckage is 6.9 meters per second from straight east, rotated 42 degrees towards the south. That deals with the resulting velocity of the wreckage. If these two vehicles come together and stick together, if their one is going 12 meters per second right before the impact and the other one's going 8 meters per second right before the impact, based off of those velocities and their masses, right after the impact, they're going to be moving at 6.9 on that 42 degree angle. As soon as they start to slide, friction's going to start to slow them down. In the proof of conservation of momentum, we talked about no external forces, so we could use that F net equals ma step. Friction is an external force. So our conservation of momentum, this math we've just done, really applies to that split second before the question to the split second after the question, before friction starts to slow things down. But as soon as they're done interacting, or as they're interacting even, friction's going to be slowing things down, so really this is kind of an estimate. And then we switch out of the momentum world. I can't use a momentum with friction to figure out how far it slides because friction's acting like an external force. Way back in grade 11, we did questions about skidding to a stop to kind of practice for this. So it's been a while, but if you can think back to grade 11, whenever we've got something skidding to a stop, there's two ways to do it. You could, skidding to a stop, sorry, getting a little bit messy there. You could figure out, based on the coefficient of friction, figure out the force of friction. When it's skidding to a stop, that's the only force, so we could do F net equals ma, force of friction is the F net, we could solve for A and then do some kinematics. That will work. Or the method I always liked was conservation of energy. The wreckage had a bunch of kinetic energy, but friction stole it away. Kinetic energy is always 1/2 mv squared. In this case, the v is our 6.9 number. That's how fast the wreckage was going. Friction steals all that away. When a force converts energy, the equation's force times distance. Since we're talking about the energy of friction, then it's the force of friction. This is what I would call a boring situation. Force of friction is going to be mu times Fn. In this case, Fn is mg. Multiply that by d. The m's are going to cancel. We get this cool equation that 1/2 v squared equals mu g d. For this particular question, we could solve, we know the speed of the wreckage, so we can solve for the distance. Perhaps another time I could give you the distance that the wreckage slid, then you could backtrack, find the speed, and then backtrack through momentum to figure out maybe the initial speed of one of the cars. It might be worth that. I think there's one of those on the worksheet. For this particular one, though, we're solving for d. It's going to be v squared over 2 mu g. The v was 6.9. We're going to have to square that. The mu that I made up, nice sticky tires, was 0.8. G is 9.8. So for this particular go, I get a nice clean, almost rounds off perfectly. The wreckage slides 3 meters. Got a little bit lazy. I used words to summarize the velocity of the wreckage. I probably could have been consistent and said, therefore the wreckage slides 3 meters, but as long as it's obvious to me after the fact that you know what you're doing, I'm not really too concerned about how you present that final answer.